Okay, so another interesting development that's connected with Pythagoras' theorem is this notion of Pythagorean triples. And closely related to that, the rational parametrization of the circle. So what is a Pythagorean triple? Well, it's just three numbers, three natural numbers which satisfy Pythagoras' theorem. Like 3, 4, 5. Or like 5, 12, and 13. Now there's in fact a whole host of such numbers, and they're kind of interesting because they correspond to triangles with integer sides which form right triangles. And surprisingly, perhaps, the ancient Babylonians, 1,000 years before Pythagoras, already wrote down lists of Pythagorean triples. And we have ancient stone tablets that people have been able to decipher, and they know that the ancient Babylonians knew about Pythagorean triples. We don't exactly know what they were doing with them, but they're written down on these stone tablets. And in Euclid, later on, we find a description of how to systematically generate these things. And it turns out that it's closely related to a relatively simple little formula. So that is m squared minus n squared plus 2mn squared equals m squared plus n squared squared. Let's have a look at that formula and see if we believe it's true. So if I expand this, I'm going to get the square of the first term, which is m to the fourth, plus the square of the last term, that's n to the fourth, minus twice the product. So minus 2 times m squared n squared. When I add this is 4m squared n squared. So the result is m squared squared, which is m to the fourth, plus n to the fourth, plus 2m squared n squared, which is what's on the right-hand side. So this is an identity. This is true for any numbers m and n. Just get by expanding it. This is an identity. And once you've seen the identity, well, then you know how to generate Pythagorean triples. You just let m and n be any numbers you like. For example, let's let m be, say, 4 and n equal 1. What are we going to get? 16 minus 1, so that's 15 squared, plus 2 times 8 all squared equals m squared plus n squared, 17 squared. So did I do that right? M squared minus n squared, that's 16 minus 1. So that's 15, yeah. And inside here is 8. Sorry, 8. 2 times m times n is 8, so 8 squared. Does that look right? So 15 squared plus 8 squared equals 17 squared. That means that there is a triangle whose sides are 15, 8, and 17, and that's a right triangle. This is very nice. And Euclid, in fact, proves that more or less all Pythagorean triples are of this form. There's one extra thing you can do. You can take a triple like this, and you can multiply all three numbers by a scaling factor. Okay, and you know, so I could multiply all of these numbers by 2, and I'd still end up with a Pythagorean triple. And so that, but that's if you include that, then that's the way of generating all of them. Now there's, that's kind of a number theoretical curiosity, but there's actually a very important piece of mathematics that's almost the same as this. Okay? And that has to do with a very important mathematical object, which was actually one of the favorite objects of the ancient Greeks, a circle. The ancient Greeks thought that a straight edge and a circle were the two most important, beautiful geometrical things. And you've all studied the circle, the unit circle with the equation x squared plus y squared equals 1. It's the unit circle in the Cartesian plane. And if I ask you to parameterize this circle, to parameterize the unit circle, almost all of you will automatically write down the following. A parameterization is, let's say, cosine theta, sine theta. Am I right? If you have to parameterize the circle, and you say theta goes from 0 to, say, 2 pi. That's a relatively modern idea. If you had asked Euclid how to parameterize the circle, he would have given you a very different answer. He would have said, well, you just apply this, surely. I told you how to do this in the elements. How? Well, this is something squared plus something squared equals something squared. If we want something squared plus something squared equals 1, we should just take this identity and divide by the right-hand side. Okay, so he would transform it into this form, m squared minus n squared over m squared plus n squared plus 2mn over m squared plus n squared equals 1. This thing squared plus this thing squared equals 1. Do we agree? That's just rewriting that identity there. Okay, and maybe he would say, well, actually you want a parameterization just involving one parameter. How could we make this into just a one parameter parameterization? Well, we could divide these fractions by suitable power of m. Okay? So let me write this, go over there. So there's two parameters there, but it's actually really just the ratio of the two parameters that matters, as we can see by dividing by m squared. So if I divide top and bottoms by m, let's say m squared better, then I will get 1 minus n over m squared divided by 1 plus n over m squared. All of that squared. And I divide the top and bottom of the next one by m squared, so I'll get 2n over m divided by 1 plus n over m squared equals 1. And now I'm going to set this n over m into just a new parameter, let's call it t. So set n over m equals t to get 1 minus t squared over 1 plus t squared, all squared, plus 2t over 1 plus t squared, equals 1. And that's suggesting that the point with coordinates 1 minus t squared over 1 plus t squared, comma, 2t over 1 plus t squared. That's always a point on the unit circle for any t. Now this is such an important thing, and it's very closely related to very keen insight of a later Greek mathematician. The later Greek mathematician is called Diophantus, who also was around 300 AD. So in the later Greek period. Question?
Does t have to be a natural number?
No, t can be any rational number.
Rational.
Yeah, because, well, the way we started, we assumed that n and m were natural numbers. And so it makes sense that we sort of think of t as being a rational number. Although, in fact, you could let it be any number at all. This identity, not complex, but any real number, and then this identity will still be valid. All right, Diophantus was looking at the same problem from quite a different attitude. So here's still the unit circle. And he was trying to parameterize the circle in another way by looking at certain lines. Okay, so this point here is -1. Let's have a look at a line, do a little bit of analytic geometry. A line that goes through this point and that has slope t. What I'm particularly interested in is what this other point of intersection with the line and the circle is. Okay, this is a high school problem. You have the unit circle, you have a line going through here with slope t. What is this point of intersection? All right, let's do this calculation. So we have to remind ourselves of some basic coordinate geometry here. What's the equation of a line if you know its slope? So there's an arbitrary point, let's call it x, y. Arbitrary point on the line, then the slope is equal to delta y over delta x. Yes? So our basic equation is t equals delta y would be y minus, so this point is really the point -1, 0. That's its coordinates. So y minus 0, that's just y, divided by delta x, x minus -1, so that'd be x plus 1. So this line has slope, or the line has equation, y equals t times x plus 1. In terms of our unknown slope t. Okay, how do we find its intersection with the circle? We just plug this into the equation of the circle, which I remind you is x squared plus y squared equals 1. Okay, so if we plug that in, what do we get? We get x squared plus, okay, y squared is that. So it's t squared times x plus 1 all squared equals 1. Okay, so there's going to be an x squared term. If I expand, there's x squared times 1 plus t squared. There's an x term. So if I expand here, I'll get 2x. So it'll be plus 2x times t squared. Plus t squared minus 1 equals 0. There's a quadratic equation. Or if you prefer to have your monic quadratic equation, we could divide by 1 plus t squared. So it would be x squared plus 2t squared over 1 plus t squared times x plus t squared minus 1 over 1 plus t squared equals 0. We're interested in what are the zeros. What are the solutions to this quadratic equation? You might say, well, it's a little bit painful because the quadratic formula is going to be a little bit messy because of all these t things and floating around. But let's say if you think about factoring this quadratic into two factors, the two factors are x minus this 0 and x minus this 0, because this has a solution when x equals minus 1. X equals minus 1 is a solution to this quadratic because this line does pass through the circle right there. It tells us that one of the factors is x minus minus 1 or x plus 1. And the other factor, let's call it x0. What's the fast way of finding out what x0 is from here? Well, to realize that when you have a quadratic equation, and you know it's two factors like this, it's x squared plus, okay, the x term is 1 plus 1 minus x0 times x, and then the constant term will be 1 minus, so it'll be minus x0. In other words, the product of the two solutions is this term right here. Does that sound familiar? The product of the two zeros of a quadratic is the constant term at the end here. So that means we can read off what x0 is. x0 is minus this. Okay? So that tells us, therefore, coming up here, that x0 is, I said minus that, so it's 1 minus t squared over 1 plus t squared. And what is y? Y is t times x plus 1, called the y0. So you have to take t times this plus 1. So it's y times, no, so it'll be t times x0 plus 1. And what will that be? Well, if this is x0 and we take x0 plus 1, x0 plus 1 will be equal to 2 over 1 plus t squared. And so therefore y0 will be t times that, so it will be 2t over 1 plus t squared. And lo and behold, we find exactly what we got the other way. Our two values give us exactly this point here. And geometrically, what does it mean? Well, that's 1, that's minus 1, that's 1, that's minus 1, that's 0. This is a line of slope t. This line has slope t. So where is t in this picture? Well, if the slope is t, it means that delta y over delta x is t. But this is conveniently equal to 1 here, this change. That's 1, so that means this must be t. T over 1 is a slope. So the meaning of the parameter t, it's just the coordinate of where this line meets the y-axis. So the parameterization is this. So if you have t equals a half, then that would be the place where t equals a half. This would be t equals 1. This would be t equals 0. This would be t equals minus 1. T equals 2. How would you find t equals 2? You'd go up here to 2, draw a line. That's t equals 2. That would be t equals 3. T equals 15 or whatever. Here t equals minus 2. T equals minus 7 and so on. This point is a little bit abnormal. It's sort of t equals infinity. That's when our point is infinitely far up there, so that the line becomes really a tangent. Now this derivation is something that all calculus students should see. Why? Because it's really related to a very important substitution in calculus, in integration theory. Let me call this angle theta. A classical theorem, goes back to Euclid, is that if this is the angle theta, then this is the angle theta over 2. The angle subtended at the center by a chord is twice the angle subtended on the circle. So that's actually theta over 2. So from this we can read off three very interesting relations. We can read off that t is equal to tan theta over 2, because the tan of theta over 2 is t over 1. And then this point, the x-coordinate, which is the cosine of theta, will be 1 minus t squared over 1 plus t squared. So that's going to be cosine of theta. And the y-coordinate is sine theta. Those are very important substitutions that are often used to rationalize integrals in integral calculus. And it's really coming from this geometry that goes back to Diophantus and arguably to the Pythagoreans. All right, so that's probably a good place to stop. So next time we're going to talk about chapter 2 of Stilwell's book. More Greek mathematics, Greek geometry. We'll see you all then. Thank you.